Let's wait 1 more minute for Caroline and we'll start. All right, so the last speaker of today is Leonardo Coregliano. He will speak about natural quasi-randomness.
Thank you for the invitation. So as it was said, I'm going to talk about natural quasi-randomness. So we already seen some talks about quasi-randomness, but let me remind you this notion. Right, so it started with the theory of quasi-random graphs, and the idea is that you want to study things that are not necessarily random, but they look random. And here it's more in a combinatorial sense. And by random, what we mean is that, at least in the case of graphs, it looks like the GNP random graph in which each edge is present with probability p. Now, the upshot of the theory is that there are several properties that you see with probability going to 1 of GNP as n goes to infinity. And when you study these properties as properties of deterministic graphs, even though the properties a priori, they look very different, it turns out that they're equivalent. So let me remind you the theorem from the seminal paper. And actually, this is actually the theorem restated in a more modern language. So the following are equivalent for a sequence of finite graphs of increasing sizes. So the first one is the actual definition of quasi-randomness that says, well, this graph sequence looks as if it was a sample from GNP, at least in terms of copies of induced subgraphs. So every time I give you some graph H and I count the number of the normalized number of copies of H in Gn, then what I see is the expected value that I would see in GNP, except for some small error that goes to 0 as n goes to infinity. Now, perhaps the most impressive equivalent. So here I'm saying that this is true for every fixed graph H, but perhaps the most impressive equivalence is that you don't actually need to check all of the graphs H. It's enough to check just that the density of induced, non-induced density of 4 cycles is the 4th power of the edge density, as you might remember from Julia's talk on Tuesday. But here I'm going to be concentrating on some other properties that, well, granted, they did not exactly appear in the original list, but they can be deduced from the original list of equivalences. And here's one that is quite curious, is unique inducibility. So what unique inducibility is saying is that, well, instead of computing the density of a finite graph H in the whole graph, I could take some induced subgraph of my graph Gn and compute the density there instead. And in unique inducibility is saying, it doesn't matter if I do that, I will see the original density, except for some error that's going to 0 as n goes to infinity. Now, of course, I should also mention that all these errors, they do depend on H. They're not uniform by any means. But in any case, unique inducibility is saying this thing, right? It doesn't matter whether you compute densities globally or locally, as long as the locally is restricted to a non-negligible set, you should see approximately the same thing. And these two things are equivalent. Looking like GNP happens if and only if densities behave, they survive taking induced subgraphs. In a different kind of vein, we have a different property that's also equivalent to the previous two, which is unique orderability. So in unique orderability, the property is as follows. You take an ordering of the vertices of your graph, and now that you have an ordering, this is now an ordered graph, so you could compute densities of ordered graphs in this guy. And so by densities of ordered graphs, what I mean is you need to preserve not only edges and non-edges, but you also need to preserve the relative order. And it turns out that if you try to compute such densities, you see something that behaves as if it was independent. So you see the density of the graph part times the density of the order part. And it doesn't matter what order you put on the vertices. So in another sense, it says that if you try to order adversarially to see some structure, you cannot do it. It looks as if you order the vertices at random. And of course, there's still this small error that goes to 0 as n goes to infinity. And in a similar vein, we have another property that's also equivalent to the previous one, which is unique to colorability, which instead of using an ordering, I now am using a red-blue coloring of the vertices, and I'm doing the same operation. So I compute densities of red-blue colored vertices. And again, what I see is the density of the graph part times the density of the coloring part, plus a small error. So in intuitive level is saying, it doesn't matter how you color the graph, it looks like you colored it at random. Now, as I said, there are several different other items in this list of equivalents that already appeared in the original paper, and several more were added, but we're going to be concentrating on these items. And the natural question that I would like to ask, and we'll see the answer, is can we generalize the above? And of course, this has appeared already in the literature for several different other types of combinatorial objects, and it was done sort of in an ad hoc manner. You have theory, quasi-randomness theories for tournaments, for hypergraphs, for permutations, but we are interested in doing some sort of general theory that we would be able to apply to general combinatorial objects, and that's the point of natural quasi-randomness. Now, of course, to apply to general combinatorial objects, we need to be able to study these general combinatorial objects. And more specifically, we need to study these asymptotically, because all of these things are saying, you have these sequences of graphs whose sizes are increasing, and we only care about what happens as n goes to infinity. So we want to study general combinatorial objects asymptotically, and that is kind of the topic of a field that is sometimes called continuous combinatorics. So this is a brief outline of the talk. It's kind of like 2 parts plus open problems. I'm going to briefly mention some concepts of continuous combinatorics, and then I'll go back to natural quasi-randomness and finish with some open problems. Okay, so continuous combinatorics, we want to study these general combinatorial objects. And of course, as you might expect from being in a workshop of model theory, for us, a general combinatorial object is going to be a model of some fixed first order theory. Of course, here I'm talking about finite models. And we are interested in studying submodel densities, right? So this is just the normalized number of copies. Now, of course, there are several different ways you can define this. You can, for instance, take this definition using P, which counts the number of unlabeled copies. You can also count the number of embeddings, but they are all linearly related, so it doesn't really matter which one you use. At the end of the day, you get similar you get similar notions, and you can transfer results from one to the other. So I will be changing sometimes which one I will be using. And for these to make sense, it's very convenient that the class of models is closed under substructures, and a very easy way to guarantee this is just to say, well, okay, the language is relational and T is universal. For our intents and purposes, this doesn't lose much generality. And you can see that this already captures several typical combinatorial objects, such as graphs, K-uniform hypergraphs, linear orders, tournaments, C coloring. So we're in good shape to be able to capture all quasi-randomness theories that have appeared so far. Well, we're not going to be able to capture all of them, but most of them at least. And let me also notice that this sort of formulation is very useful for talking about problems in extremal combinatorics, because you can just add axioms to forbid some substructures if you want, like considering triangle-free graphs or Turing-like problems. And another kind of operation that's going to be very useful for us is to take this joint union of universal theories. And by this joint union here, what I mean is that I take the disjoint union of the languages and I put both of the axioms. So in other words, models here, it is as if I had 2 models on the same vertex set, one of each theory, but the vertex set is the same for both of them. And the reason this is important is because, for example, if I give you some theory P and I take the union with the theory of C colorings, models of these theories, you can see them as just models of T that have a C-coloring of the vertices, so C-colored models of T. And if I take a union with linear orders, that's just ordered models of my theory T. And if you remember the first slide, these things will be useful, right? Now, the idea of continuous combinatorics is we want to study these densities when this target model here is very large. So the question is, can we instead encode this in some sort of limit object in which these densities are naturally defined and somehow encode the sequence that I will be studying? Now, not every sequence will be able to have some sort of limit, and the name is already suggestive. Limit requires some sort of notion of convergence, and this is the notion of convergence that is very natural for these kinds of problems. You say that a sequence of combinatorial objects or models of a fixed first order theory or first order universal theory is convergent if the sizes are going to infinity or even strictly increasing. And for each fixed model M, the density of this model in my sequence is giving me a convergent sequence of numbers, right? So for example, if I take theory of graphs, what I'm saying is that I require the edge density to be convergent, the triangle density to be convergent, the density of two paths to be convergent. Every finite graph needs to have density converging in the sequence. And the question rephrased here is, if I give you such a convergent sequence, can I encode the limit in some sort of object in which there's a natural definition of these densities that are capturing these limit values of my convergent sequence? Now, if you know a little bit about this theory, you might know that one of the first examples that appeared of such limit theories is that of Graphqls. So this was done for theories of the universal theory here is the theory of graphs, and it produces limits of dense graph sequences. And these are just measurable symmetric functions from the square to the interval. And the idea is that it's kind of like an adjacency matrix of a graph over the interval, except that you have fractional edges, and these should be interpreted as the probability that two vertices are connected. And if you have this intuition in mind, it's very easy to cook up a formula, a very natural formula that gives you the density of a finite graph in a graph on W by just doing some integration. And the main theorem of this theory is that this actually is capturing limits of convergence sequences of graphs, in the sense that, every time I give you a sequence, there's a graphon that converges, to which the sequence converges. And if I give you a graphon, then there is a sequence that converges to this graphon. So it's a two-sided existence, if you will. Now, of course, because we're going to study general combinatorial objects, the question that we ask is, can we do this for general universal theories? And the answer is yes. There are several different ways of defining limit objects for general universal theories. So here are some, I guess, 5 names that have appeared, and they have very different natures, but I'm not going to get into details on what are their definitions. And I will just say that some of them are more geometric, and you can see vertices and pairs and etc. inside them, whereas some of them are more algebraic, which are easier to manipulate and even use computer programs to deal with them. And also there's sort of a difference in terms of like how finite or infinite they are, in the sense that, for example, ultra products, they're very well connected with the convergent sequence that is converging to it. Whereas these objects downstairs, the connection is a little bit weaker. But I will not get into details on these limit objects. I'm more concerned about applications on this talk. And the reason why you should care about these kinds of limit objects is, of course, even though they are interesting objects in their own right, they are useful to actually pushing back results. You prove some result in the limit, and then you push it back to the convergent sequences or even non-convergent sequences. And some examples of things that have appeared in the literature, you can do regularity lemmas, for example. So you can prove regularity lemmas in the limit are very easy to prove, and then you can use some non-standard analysis tools to pull them back to the finite. Of course, you get inefficient versions, but in any case, you get them very easily. Extremal combinatorics results can be derived using these theories, particularly like the left side of this branch is very, very successful in dealing with extremal combinatorics. And of course, the topic of the talk today is quasi-randomness, which we'll be talking about. So let's go back to quasi-randomness then, and let's review what does graph quasi-randomness look like in this limit version, like using Graphqls. So if you remember, the definition of quasi-randomness was saying that densities in Gn should look like GNP. Well, it turns out that GNP is a convergent sequence with probability 1, and the graphon to which it converges is the constant P graphon. So another way of stating quasi-randomness is to say that my sequence actually converges to a constant function. It's up to 0 measure, so that's just a small technicality that arises, but this is actually the definition of quasi-randomness in the limit. It's just that the limit is a constant function. Unique inducibility, it's something like this. You say every time I look at a non-negligible subset of vertices, if I look at the sequence of induced subgraphs, then it converges to the same limit, right? So I start with some sequence converging to W, and if I look at any subset of vertices that I pick along my sequence, as long as they're non-negligible, it gives me another convergent sequence that converges to the same limit. And a priori, there's no reason why the limit needs to be constant, but the theorem is saying, yes, the only limits that have this property are the ones that are constant functions. Unique orderability is a little bit more complicated. Here's how it looks like in this limit. I give you 2 sequences of order graphs, and let's assume that if I forget the order, they converge to the same limit as graph sequences. Then unique orderability says that they need to converge to the same limit of ordered graph sequences. That's what unique orderability is saying. It says, doesn't matter how you order, there's only one limit of ordered graph sequence. Once you know the graph limit, then you will know any kind of ordering you put, you always get the same limit of ordered graphs. And similarly, unique 2-colorability, I give you 2 sequences of 2-color graphs. And as long as the graph part converges to W and the coloring has the same proportion, this is just a small technicality that's different than orderability, then they must converge to the same limit of colored graphs now. So we want to generalize this to arbitrary combinatorial objects, or more specifically, models of a fixed universal theory T. But notice that if you're thinking a little bit on more this model theoretic side, notice that these last 2 items are actually changing the theory, right? We start with the theory of graphs, but somehow we go to theory of ordered graphs and theory of colored graphs. And in fact, this one is also changing the theory, but it's slightly less trivial to see that the correct way of formulating this actually should change the theory as well. So we need to see how these kinds of densities and these kinds of limit objects interact with moving information around between theories. And the natural concept to consider here is that of open interpretations. These are also sometimes called definitions in the literature. So an open interpretation from T1 to T2 is just a function that maps each predicate symbol of T1 to some open formula of T2. So an open formula is also called a quantifier-free formula. And you also want that axioms of T1 get mapped to theorems of T2. So let me give you some very simple examples of, let's start with some trivial examples. So if you add some axioms to a theory, so for example, you go from the theory of graphs to the theory of triangle-free graphs, you can always interpret the theory of graphs inside this because, just map it identically, and axioms are also axioms of the other guy. So this gives you a very trivial interpretation of one and the other. Another kind of trivial interpretation you have is, remember that we could do these joint unions of theories, right? So models of this theory, they were models of T1 and T2 at the same time over the same vertex set. So, and the way that you interpret theory T1 inside this is just say, well, ignore that you have T2, just map identically. And of course, all axioms are still axioms of this joint union theory. And for a less trivial example, the interpretation of triangles of a graph, you could interpret the theory of three hypergraphs inside the theory of graphs by declaring the hyperedge to be exactly triangles in the graph. Now, this is very suggestive because there's a natural construction associated with this kind of interpretation, right? So if I give you a graph, this open interpretation is suggesting the way that you should construct a hypergraph, a tree hypergraph from this is by considering an edge every time you see a triangle, right? And this happens for any kind of open interpretation. You have this natural contravariant construction where if I give you a model of T2, you can just construct a model of T1 by declaring the vertex set to be the same and declaring the predicates to be exactly the places where the corresponding formula is true. Now, the nice thing about these open interpretations is that they behave very well with respect to convergence and limits. Namely, if I give you a convergence sequence, if I interpret the sequence with some open interpretation, then this gives me a convergence sequence in the other theory. And moreover, I did not get into details how you define the limit objects, but all these limit objects that have appeared, there's a very natural operation that you can do to the limit object that actually captures the limit of the new convergence sequence. So it's a sort of a natural operation also with taking limits. It's sort of, you can think of it as if it was a commutative diagram, but not exactly. Now, why do I care about these open interpretations? Let's go back to quasi-randomness and think about it for some time. And let's see, well, we had this construction that took this joint union of theories, and every time I had such a thing, I had these trivial open interpretations to these guys. And as I said, this gives me functions in the other directions that allow me to take limits of the union theory and map it to limits of each of the theories by just forgetting the other part, essentially. Now, if you think for some time, well, okay, so every time you have diagrams that look like this, this thing on the right, that gives you a very natural definition of couplings, which is, if I give you an object here and I give you an object here, a coupling is just an object here that maps to these two guys, right? So that's the definition of coupling of a limit of T1 and a limit of T2. Now, I didn't get into the definitions of these things, but if you work out the definitions and you think about it for some time, you will see that graph quasi-randomness was actually talking about existence of only one coupling in the following sense. Unique orderability, what it was saying is that I gave you some graph limit such that it doesn't matter how you order it, you always see the same limit of ordered graphs. In other words, there exists only one coupling with the linear order, right? There's not more than one way of coupling with the linear order. And similarly, unique two-colorability was saying the graph limit only had one coupling with any two coloring limit. So these graph quasi-randomness notions, they have very natural definitions in general that don't really depend on being for graphs, right? There's no graphs here. You could plug any universal theory, and these notions of existence of existence of a unique coupling with a certain other limit object still make complete sense. So with this in mind, we can actually generalize graph quasi-randomness, and we can prove a theorem that is that's much more general, that says, if I give you an arbitrary universal theory T and I give you a limit of this theory, then if this guy is uniquely couplable with any limit of two colorings, this happens if and only if it's uniquely couplable with the linear order. This is not a particular thing about graphs. This is true in general. And in fact, it's true that it's uniquely couplable with things that are much more general than just colorings and order. It's uniquely couplable with any limit of rank at most one. Now, I'm not going to get into details exactly what rank is. It's some notion that you can define of limits, but let me give you some examples of things of rank at most one. So permutations, cyclic or linear orders, C coloring, so not only two colorings, but any number of colors, and graphs with bounded VC dimension. They all give you limits that have rank at most one. Now, just as the usual quasi-randomness, graph quasi-randomness theorem, there are more items in this theorem, but I'm not going to get into details because they involve definitions that I am not covering here. And you know, if you're reading these theorems, you might have noticed a 1 here, and the reason why there's a 1 here is because actually you can further generalize this and plug an L there. In fact, we can talk about unique couplability with things of rank at most L, and this is equivalent to being uniquely couplable with any quasi-random hypergraph in arity at most L. So another way you can see this is you can think that a limit object is trying to tell whether the object is random or not. And if you have rank at most L, you will think that this object is random if and only if all the quasi-random hypergraphs of arity at most L think that this guy is random, right? So this is what U couple L is actually saying. Anything of rank at most L think that this guy is random. And again, I didn't get into details of what rank actually is, but here are some examples of things of rank at most L. So if all predicates have arity at most L, you have rank at most L. Orders on L tuples have rank at most L. And if you remember Henry's talk yesterday, K hypergraphs with finite slice-wise BCL dimension will have rank at most L. And that, of course, as I said, there are more items in this equivalence, but I'm not going to get into detail. Now, you might be wondering what happened with the other items. There were 2 other items that I mentioned in the first slide. You can also generalize those. So the item that said constant graphon, it's generalized to a notion called independence. This has nothing to do with NIP, is a different notion. And unique inducibility, there's also a property called U-induce. And again, the reason why there's a 1 here is because there's actually a version that is on higher arities. But let me also say that for the graph case, these things are equivalent as said by the graph quasi-randomness theorem, but for general T, this is not the same, and it's actually gives you a hierarchy of properties, which are sort of expected if you know a little bit about hypergraph quasi-randomness. You don't get a single notion of quasi-randomness, but you have different levels of quasi-randomness, and in fact, it's a poset of quasi-randomness. Now, let me also briefly state some other terms that we can prove about these properties. So first is why we actually call these things natural. So if P is any of these properties that I've said, they're actually preserved under open interpretations. This means that if you look at this property on a certain theory and there's a random, something that's being declared to be quasi-random in this theory, if you apply an open interpretation and move it to another theory, it will still be random in the other theory. So it's preserved under open interpretations. It's a proper hierarchy in general, so you don't have any upwards implications. U couple implies U induce, but U induce doesn't imply U couple. This is actually very easy to see because linear order is clearly uniquely inducible, because you take any subset of linear order, it's still linear order, but it's clearly not uniquely orderable. And U couple, independence implies U couple, and the other direction is not true. Well, since I didn't get too much into details on independence, I'm not going to really spend too much time, but there are some still open problems about this, because the separation is not as strong as we would expect. Now, I will also say, we saw the big characterization of the U couple property. There's also a characterization of the U induce property, but since I didn't really define how it looks like in general, I'm not going to get into details. Now, let me just finish with some open problems. So we saw this notion of unique couplability, and there's a very natural analogy between unique couplability and independence of random variables. So when you say that 2 limits are uniquely couplable, it behaves as if it was random variables that are independent, because when you compute densities, you see the product of the densities. But of course, for independent random variables, we know that if I give you pairwise independent random variables, it's not necessarily true that they're tree-wise independent. But for unique couplability, so far, we don't know of any examples that this happens or cannot happen. So this is still an open problem, whether pairwise unique couplability implies mutual unique couplability. And I briefly mentioned that the relation between U couple and independence is still not completely clear, but since I didn't get too much into the details of definition, I'm not going to say too much about it. And let me also say that most of the quasi-randomness theories that appeared already in the literature that can be rephrased in this universal theory framework, when you look at the quasi-random object that they define, they sit somewhere in the hierarchy that I told you about today, with one very prominent exception, which is the quasi-random permutation, or the limit of the quasi-random permutations, and it does not even satisfy the weakest of our properties. So the kind of philosophical question I would also like to raise is, why do we really think that this guy is random? What is the natural quasi-randomness property that this guy satisfies? And that's all I had to say for today. So thank you all.
Thank you very much. Any questions? People online?
Can I ask a question? So you mentioned this connection to bounded VC dimension. Does stability appear in any as any meaningful property?
At least not for these properties a priori, because what really matters, this notion of rank. So I'm not entirely familiar with the definition, but I think the notion of rank is somewhat related to the notion of D dependence or L dependence. And once you have stability, of course, you have bounded VC dimension. And at least for U couple, that's sort of already does the trick, right? But it's certainly a natural question to say, well, maybe you want to say something about, instead of saying let's take unique couplability with everything of rank at most L, maybe I want unique couplability with everything that's stable or whatever.
Yeah.
Right? Which is also a very natural question. But somehow I would feel that just this characterization of saying, as long as colorings already think that you're random, everything of bounded VC dimension is going to think that you're random. Then probably, once you're saying, take all stable graphs and they think you're random, this sort of already implies that all colorings think you're random, and then you already get NIP thinks you're random, right? And I would imagine this also happens for higher rarities, so it shouldn't make much of a difference.
Thanks.
Any other questions?
Can we look back again at this big U coupling? U coupling.
Yes.
One more time.
This version or the one version?
Maybe this version. Yes. So perhaps it's also a naive question. So does it seems that so this notion of K quasi-random, it would be equal to or L quasi-random, somehow it would be equivalent to L quasi-random if you are looking restrict to certain kind of like structure. So okay, it's a very vague question, but somehow does the idea of K hypergraph with finite VC dimension means if you are restricted to a structure bar, you still should see this randomness. Okay. Maybe my question is too vague.
No, so let me first say, when I say a quasi-random K hypergraphon, what I mean by quasi-random K hypergraphon is the top quasi-random one. So it's the one where you put each K edge with certain fixed probability P, right? So this theorem is saying, if you consider all the arities up to L, right? So you consider 1, 2, etc., and in each of these arities, you take the quasi-random graph on that arity, and you hit it against your object. And all of them think that your object is random in the sense that there's a unique coupling. Right? So you're able to fool all of them in a certain sense. If you're
Right.
able to fool all of them, you will be able to fool anything of rank at most L, or in particular, you will be able to fool, say, K hypergraphs with bounded DC dimension, right?
Right.
So the way of thinking about this is that they cannot see any structure, right? So they're saying this object, if there is structure in this object, is way beyond what I can see, right? Think of the easy case where you say, well, imagine that a graph is not random. One way you could try to show that it's not random is you say you color some part with red vertices and say, oh, but here's a clique that I shouldn't be able to see, right? Because if it's random, there shouldn't be a linear size clique, right?
Okay.
Something like that, right? But the random guy, you cannot do it. It doesn't matter how you try to color, it always looks random, right?
Okay.
But notice, right, that's, you know, if I give you a random graph, but you're allowed to use graphs, then you can just put the same random graph that I gave you on top of it, and you would see structure, right? So randomness has a certain limit, right? That it stops being random or something, right? Unless you're a trivial object, and then it sort of looks random always because of trivial reasons. But that's kind of the intuition of this version of quasi-randomness. It's saying absence of structure.
I see. Thanks for answering.
Yeah, so it kind of reminds me, there's a notion of like collapsing indiscernibles in model theory. So I don't know what the connection is, but there is such a characterization due to Artem and co-authors of the VCL dimension. And I wonder, I think maybe people are, or maybe one way of phrasing the same question everyone else asked would be like, if you somehow if you restricted the class, changed what you were testing and asked for a notion of quasi-randomness that only worked for like a subclass of structures. So if you only asked for trees to think the class is random.
Yes, so yes, this is certainly possible. You can just ask, right? I give you a collection of limits, and what are the things that are uniquely couplable with these, right?
Right. Yeah. So, like for example, like one question I was thinking about is like, there's this correspondence between like weak hypergraph regularity and like linear hypergraphs.
Yes, this is very much related. So these notions of L localities that are omitted, this is very much related to this.
Okay, I see. So you can kind of detect those differences with this machinery or something.
Yes, yes. So I can briefly say about L locality. So L locality, which is also equivalent to this, is something like this. Imagine, so you can, another way that you can think about computing densities in these limit objects is that you can sample a countable object. If you know how you do this for graphons, it's something similar, right? And then you can ask about events of this countable graphon, right? And you can do, so if you think about graphs, you could do an event that, a bunch of events on some subsets of natural numbers, and U couple one is equivalent to saying, as long as the sets you pick have pairwise intersection of size at most one, these events are going to be independent. And L locality is saying, as long as intersections are at most pairwise intersections have size at most L, they're going to be independent. And this is very much related to what happens with hypergraph.
With linear, I see.
Yes, exactly, because linear hypergraphs is going to be the one case.
Yeah, I see.
And the hypergraph quasi-randomness case, if you know clique discrepancy, that gives you the L linear hypergraphs. But this is a version that is even more so because you're not talking only about the edge, but you're talking about any sort of event.
Sure.
You could sample, you could say, well, I want these vertices to give me something that is isomorphic to this model, and these vertices to be something like that. And this is what is actually equivalent to U couple L.
Okay. Okay, yeah, great. Yeah, that's really interesting. Very timely.
Yeah, and on the
anyway, I'm getting an indication that I'm supposed to wrap it up.
Oh, okay.
From my, is that what you were saying? Yeah. Because right, the talk started at, yeah, I guess we're a little over time, so maybe maybe I will give the microphone back to the chair of the session.
Well, I guess we don't have time for any last question, but let's thank Leonardo again. We will be able to contact him for further discussions, and will we resume tomorrow at 11 for the last day of the conference, the workshop.